Welcome back. And now we're going to learn about some balanced and unbalanced free body diagrams. So in Newton's three laws of motion, you were starting to see how I was able to use free body diagrams to show different types of motion and also to illustrate the forces acting on an object. So what we're going to be learning about here is the difference between a balanced and an unbalanced free body diagram. So we already learned about how to draw a free body diagram, so let's look at what this means if something is balanced or unbalanced. So let's say that right now we have a boat that's floating in the water and there is no motion. Now, if there's no motion, that doesn't mean that there's no forces. There are still forces acting on the boat. So here is our free body diagram of our boat. Now, the boat has weight to it and it also has people in the boat. So right here, I'm going to draw a downward arrow. Whenever we draw arrows, so from this point forward, it's super important that we label the arrow. So this one is going to be the weight of the boat. So that's a downward force. But the force, or this diagram right now, if there's only a downward arrow, it would mean that this boat is sinking down. But it's not sinking down. Again, remember, there is no motion happening. And so therefore, there must be a force in the opposite direction of the weight of the boat. And that means that there's got to be one in the upward direction. And it has to be the exact same size since it's not moving, since there's no motion. Well, you might have guessed it, but this is the force of the water. So in order for this boat to be floating, the water is pushing up on the boat, and the boat is also pushing down on the water, but they cancel each other out, and they're pushing on each other equally and in an opposite direction. So it'd be like kind of like if you went up to your friend and you were pushing on your friend, but they were pushing on you back, you'd both be exerting a force, yet you might not be moving as long as each of you have the same strength. And in this example, there's no motion because the weight of the boat is being compensated or being resisted against by the force of the water. So let's take a look at this rock. Okay, let's look at the rock. Now the rock is not moving, so again, we have no motion. Now, it's sitting on top of my my coffee mug here, and so the rock has weight. So let's say that we have the weight of the rock. And the weight of the rock is not too much for this water bottle. This water bottle, or this coffee mug, is able to also hold up the rock. So what we would do here, since this rock is not moving, we need to show that there's also a force in the upward direction that is resisting the weight of the rock. And this here we could say is the force of coffee mug. Okay. So, for both of these free body diagrams, there's no motion happening. And the best way to see that there's no motion happening in the free body diagram is that the upward arrow is exactly the same as the downward arrow. The upward arrow is exactly the same as the downward arrow for both of those. And so in these examples, we'd say there is no motion because they are equal and opposite. So they're resisting each other. Let's go on to a little bit more of a complicated example. Let's say we have this car, this super sweet modern looking car here is going in the forward direction, and let's say it's traveling at 100 miles per hour. So since we know it's moving in the forward direction, let's just start by putting a forward arrow, and let's write this is the speed of car. Since we know the speed of the car, let's also include the speed of the car, which is 100 miles per hour forward. Now, the car is not falling through the road, and it's also not flying. And so there's more than just the forward motion of the car and the speed of it. So we need to show that the car has a certain weight to it. And so we're going to add a downward arrow, and we'll write the weight of the car. But the car is not moving down, so there has to be, it's not moving through the road, so therefore there must be an opposite force to the downward arrow. So that means that we have an upward arrow, and this would be the force of the road. Now you can imagine that if we tried to take this car into the water, the weight of the car would be more than the force of the water, so it would actually travel through the water. But the road is strong enough that it can hold up the car. So we have the speed of the car going forward, we have the force of the road holding it up, and the weight of the car is keeping it on the road, or we could say the gravity that's pushing the weight of the car onto the road. But then also as it moves 100 miles an hour, I don't know if you've ever put your hand out the car window, but there's also going to be some air friction as well. And there's also going to be some friction on the road as the tires hit the road. So there is some backwards force. So if we were to then add up all of these arrows, we could say that there's an upward force and a downward force, which cause there to be no motion in the up and down direction because those are equal. But if we compare the forward direction with the backwards direction, you can see there's a lot more forward direction than there's backward direction. So the overall direction is to the right. So let's say motion to the right. Okay, so now we have motion happening, and this is because this one arrow has some extra force that's left over that causes it to have motion in the right direction, in to the right side of the screen. All right, let's then look at a tennis ball that is being rolled across a table. So again, the table is holding up the tennis ball, but the tennis ball has mass. So let's say that we have an upward force of the table, and there's also the downward force of the tennis ball, but we can call this the weight of the tennis ball. Now, if you roll this across the table, it will eventually stop because there's some friction between the ball and the table. So let's say that this is the friction, which is going to slow it down, but it's overall moving forward, and so we'll say that this is the push that was applied to this tennis ball. So again, if we add up these arrows, we have an up arrow that's equal to the down arrow, and we have a backwards arrow that is smaller than the forwards arrow. So the overall direction of this tennis ball would be this much forward, so we would have motion again. So again, remember, we were learning about balanced and unbalanced free body diagrams. So looking at these different arrows, you can see that if these two arrows are equal in size and opposite in direction, then they are balanced. If they are equal in size and opposite in direction, they're going to completely resist each other, and there's going to be no motion, so therefore they are balanced. So if you ever see a balanced free body diagram, that means that there is no motion. If you look at the arrows on a free body diagram and they are unbalanced, meaning that one arrow is bigger than another arrow, then that means that there is motion, and we would call this an unbalanced free body diagram. Again, down here we look at the arrows, and the arrows tell us that there is motion because they're not equal in size, but they're opposite in direction. So we know that this arrow is going to cancel out a little bit of the forward motion arrow, but there's more forward motion than there is resistance. So therefore there will be motion, and therefore this is another example of an unbalanced free body diagram. So on your page, on your Science Notebook page, what I need you to do is to draw a balanced free body diagram and an unbalanced free body diagram. So at the top of your page, write balanced free body diagram, and then draw an unbalanced example of a free body diagram. Now you can use an example from this video lecture, or you could come up with your own example, but you need to show the free body diagram, and then you also need to show the arrows. You need to show the calculation of the arrows. So therefore, these ones should be equal and opposite, and these ones should have one that is larger than the other because it's unbalanced. All right, I'll see you later.